Your pancreas does way more than you think. Most people know the pancreas makes insulin for blood sugar control, but that's only half the story. One side, the endocrine pancreas, makes hormones like insulin and glucagon to manage energy. The other side, the exocrine pancreas, makes digestive juices that break down your food. These two systems are tightly connected. If one stops working, like in diabetes or pancreatitis, the other often struggles too. That's why taking care of your metabolism with healthy eating, movement, and giving your body breaks between meals helps protect both digestion and blood sugar. To watch the full lecture, click the link in my bio. Looking to improve your own metabolic health? Visit insuliniq.com for courses, coaching, consultations, and a 10-day free community membership trial. To dive deep into the science behind metabolic health, become an insider at benbikman.com, where you'll enjoy my exclusive content, ad-free podcasts, live stream Q&A access, and more. Welcome to the Metabolic Classroom. I'm Professor Benjamin Bikman, a biomedical scientist and professor of cell biology. Everyone, thanks for tuning in. Thanks for being my honorary students for another one of these mini lectures where we just consistently unpack the fascinating topic of human metabolism. Today, we're diving deep into a topic that is central to both digestion and metabolism, or nutrient control, nutrient metabolism, and that is the endocrine and the exocrine pancreas. That might be a term you've never heard before, but it is a testament to how remarkable and unique the pancreas is, because this remarkable organ does double duty. It releases hormones into the bloodstream, in that these hormones thematically manage nutrient metabolism, but that's the endocrine part. What about the exocrine? Well, that is where this double duty organ also dispatches digestive juices and enzymes into the intestines to help break down our food. In other words, the pancreas works to digest those very nutrients that it then will help regulate as it secretes hormones into the bloodstream. In this episode, we'll explore the key products from each side, endocrine and exocrine, as well as their actions and even how they interact in some pretty interesting ways. As much as we often discuss these two aspects of the pancreas, endocrine and exocrine, as being very distinct, they absolutely are connected. So whether you are a student, a health enthusiast, or you're just curious about how your own body works, I actually think you're going to come away from this mini lecture with a much greater appreciation for the pancreas as a metabolic multitasker. Now, before we get into function, let's just talk about the anatomy and the structure of the pancreas. The pancreas sits within the body, tucked behind the stomach. It's not too big. It stretches to around 20 centimeters in length. And structurally, it has three parts. It has what's commonly called the head, which is near the beginning of the small intestine. Then there's the body of the pancreas. And then there's the tail, this wrapped around tail, which is over near our spleen. But the more important division is between its exocrine and endocrine tissues. It's less of an anatomical distinction in the organ. Now, about 98% of the mass of the pancreas is exocrine. So these are the cells that produce the digestive enzymes, as well as bicarbonate. Yes, in fact, the very bicarbonate you may use in your baking. Just 1 to 2% of the pancreas is made up of the endocrine part. And this is made up specifically of these areas called the islets, or these small little islands of cells called the islets of Langerhans, named after the individual who discovered them. And these are heavily vascularized, in other words, lots of blood flow. And they're regions with lots of blood flow, which allows a very rapid hormone release into the blood. One fascinating design detail is that blood flows from the islets into the surrounding exocrine tissue. So endocrine hormones like insulin can influence digestion directly. This is sometimes in physiology or anatomy, this is sometimes referred to as a portal, where you have an artery, which is coming from the lungs and all of its oxygen and nutrients. It will separate into capillaries to feed some cells, and then usually it will then come back to the heart and lungs. So it has one pass through one cell type and then it comes back. But when you have a portal system, you have the blood vessels separating and feeding cells and then going in to feed another set of cells and then coming back to the heart and lungs. So this is a portal. It's a portal-like arrangement where we have this elegant managing of two functions really needing to work, needing to coordinate their efforts together. That's usually what a portal system is going to reveal. It's that you need to send one signal to another part before it runs back throughout the entire body. In other words, you don't want to wait that long. You want to send the signal much more rapidly. Okay, now let's start with, now that you have a general overview of the structure and the anatomy of the pancreas, let's start with the endocrine pancreas. And that is coming back to the islets of Langerhans. The islets contain several types of hormone-producing cells. The most famous, beta cells. They make up about half of the islet, and of course, they produce insulin. Then you have alpha cells, which secrete glucagon. You have delta cells that release a hormone called somatostatin. And then you have pancreatic polypeptide coming from the PP cells. In fact, those cells are named for their product, the pancreatic polypeptide, PP. And then you also have ghrelin. Though most ghrelin comes from the stomach, there is some contribution of the epsilon cells in the pancreas. So we have all of these products coming from the endocrine pancreas. Now, these hormones, of course, do not act in isolation. They communicate constantly, both through local paracrine signaling and through input from the nervous system. Now, let me just share some thoughts on the paracrine aspect. When we use the term paracrine within the realm of endocrinology, that is distinct from endocrine. Endocrine is when you release a hormone into the blood to then go affect other hormones, other cells rather. So one cell type is releasing a hormone, it flows through the blood to some other faraway cell to tell that cell to do something. That's not what we have happening in the islets, these small little neighborhoods of cells where you can have one cell releasing a hormone that doesn't need to get into the blood. It immediately goes right next door to a different cell, like the beta cell releasing insulin, going right over to the alpha cell, which would be releasing glucagon. That's paracrine signaling. All right, so that's important to appreciate, that there's a lot of signals going back and forth across all of these cells within the islets, never even needing to go into the blood. They're just operating in a paracrine fashion. One of the hormones I just mentioned was somatostatin from the delta cells. Somatostatin can directly dampen insulin from the beta cells and glucagon from the alpha cells. So somatostatin wants to operate as a brake on both of those. And then, of course, meanwhile, we have the sympathetic nervous system, the topic of last time's metabolic classroom, which is going to boost glucagon and inhibit insulin, whereas we have the parasympathetic, which is going to, in turn, boost insulin. So you also have that direct sympathetic innervation where you have neurons coming right to the islets, telling the islets that, hey, the brain wants me to tell you to do something, and so I'm going to do it. All right, now I mentioned the name of the hormone, so let's briefly go through the function, especially of the key ones. So insulin is the master metabolic hormone. It is the body's storage manager. Released in response to typically rising glucose after a meal, insulin will help tissues such as muscle, fat, to pull in the glucose. But even in other tissues like the liver, it helps the liver know what to do with that glucose. And indeed, it promotes glycogen storage in the liver. It will inhibit the breakdown of that glycogen. It will inhibit the production of new glucose, gluconeogenesis. And of course, it very, very heavily encourages fat storage, mostly by inhibiting lipolysis. But insulin also supports protein synthesis by helping the muscle cells maintain their muscle protein by inhibiting the breakdown. But problems arise when insulin is chronically high, of course, something that you've heard me talk about abundantly. Diets that are heavy in refined carbohydrates or constant snacking of those refined carbohydrates keep insulin elevated, and over time, cells will simply stop responding effectively. This insulin resistance forces the pancreas to work harder which can lead to type 2 diabetes as either the insulin production goes down or at the same time, I should say, and or the body continues to just be very resistant to that insulin. Glucagon is insulin's counterbalance. It's the yang to the yin. When blood glucose falls, whether from fasting or prolonged exercise, glucagon signals the liver to release glucose from glycogen and to make new glucose through gluconeogenesis. It will also promote fat breakdown, once again having an opposite effect to insulin, which is then going to be freeing fatty acids from the stored fat cells. What was stored as triglycerides are now getting broken down into free fatty acids. So again, that isn't as much as we focus on how insulin and glucagon are having opposite effects at the liver with regards to either promoting glycogen or breaking it down, respectively, we also see opposing effects at the fat cell. Insulin wanting to inhibit lipolysis, glucagon wanting to stimulate it. Now, together, they each play a part. Insulin and glucagon create a push-pull system, if you will, that helps maintain metabolic stability. They maintain homeostasis. And one good example of this is just fasting. During fasting, insulin levels drop because blood glucose levels come down, and then glucagon rises to make sure that the glucose doesn't go too low. At the same time, this shift, insulin down, glucagon up, increases the mobilization of fat, so lipolysis, and the fat burning, beta oxidation, as well as the production of ketones to help offset the need of the brain in particular for glucose. This natural flexibility is, of course, diminished in insulin resistance, where insulin stays elevated and glucagon is not going to be able to do what it wants to do. So we're trapping the body into an energy storage mode. Now, I'd mentioned, for those of you who are paying attention, you're wondering, what about the other hormones? Okay, I'd mentioned somatostatin. Somatostatin does serve as a modulator. It wants to inhibit both insulin and glucagon. It keeps them in check. It prevents them from going too high. So you could say that somatostatin acts as kind of a babysitter. It helps smooth out what might otherwise be too dramatic of a peak. So it's kind of like a metabolic brake pedal. And then pancreatic polypeptide will contribute to satiety signaling. And in fact, this is one of the hormones that may be leveraged in future satiety-focused drug therapies to help with weight loss. And then ghrelin is a hunger hormone, so it's acting in opposite. It also comes from the Epsilon cells, yes, from the stomach, as I noted earlier, but it wants to stimulate appetite and actually stimulate growth hormone release. Now, these most recently mentioned hormones aren't going to be as famous as insulin, certainly, and not even as famous as glucagon. But disruptions in their signaling can contribute to overeating. Like if you're not making enough pancreatic polypeptide, hunger will be up. If you're making more ghrelin, hunger will be up. It can also affect digestion and just contribute to some of the metabolic mayhem that we see in problems like type 2 diabetes, where the islets are just a little disrupted in the population of cells they have. Okay, that is, I think, a sufficient primer on the endocrine pancreas. Let's transition now to discuss the exocrine pancreas. That is the digestive powerhouse. Each day, the exocrine pancreas, all of those cells of the pancreas that make these digestive enzymes, it actually secretes up to 1 to 2 liters of a very alkaline, enzyme-rich fluid, all of this, what we call digestive juice, into the small intestine. Now, I say it's alkaline. That means it's basic chemically, or its pH is high. That's because of the bicarbonate. It's like that baking soda. The bicarbonate neutralizes stomach acid. So think about how the stomach has this really acidic mix, and it is going to start dripping into the small intestine, which doesn't have that big mucus protective lining that the stomach has. So how do we prevent that acidic mixture from coming into the small intestine and ripping right through it? Well, we negate it. We neutralize it with this bicarbonate-rich slurry of digestive juices coming from the pancreas. So it helps create the right pH environment for the enzymes to function and just to protect and maintain the anatomy and the function of the small intestine. Now, what about the enzymes? So these enzymes break down the three major macronutrients. For example, the pancreas is releasing amylase into the small intestine. Well, that's going to help us digest starches, so carbs, into its simple molecules like glucose and fructose. The pancreas also releases lipase enzymes. Lipases you can hear that probably what it does. It will help digest triglycerides. It takes that big three fatty acids bound to glycerol molecule and starts pulling off the individual fatty acids and then the glycerol. And that's going to also, of course, do that with the help of bile and another enzyme called colipase. So bile is what helps split up all the fats, and then the lipases from the pancreas are going to come in and actually do the kind of individual trimming at the level of the molecule itself. But then we also have protein, and that's where the proteases come in. Proteases like trypsin or chymotrypsin and carboxypeptidase. These are enzymes from the pancreas that digest the proteins. Now, interestingly, when it comes to these proteases, they're actually secreted from the pancreas they get secreted in an inactive form called a precursor. Zymogens, they're referred to in that family of zymogens. And that's just to make sure that the pancreas actually doesn't digest itself. Because imagine if you were releasing an enzyme that could break down proteins. Well, what if you start breaking down the proteins in your own cells, in your cell membranes? So they don't get activated until they actually reach the intestines, where there's a particular enzyme called enterokinase, which will then start converting trypsinogen, which is what the pancreas actually makes. It converts trypsinogen to trypsin, and then trypsin will activate the rest. So it's a pretty clever system to make sure that the pancreas isn't compromising itself. Now, problems here quickly show up as malnutrition. So if you got a problem in your ability to digest food, you're going to start starving, even if you're eating. Like, for example, cystic fibrosis. That in that instance, defective bicarbonate secretion thickens the pancreatic juices and it blocks the enzyme release. But also, if you have a chronic inflamed pancreas or pancreatitis, then you can have destruction of the exocrine tissue, which causes most commonly fat malabsorption. You can't digest your fat. In such cases, of course, what you've got to do is put those enzymes back in. So you have pancreatic enzyme replacement therapy becomes essential just for the person to survive. Now, let's talk about the regulation of the exocrine pancreas, because there's three overlapping phases here. The first is the cephalic phase. That's a phase it's almost like Pavlov's dog, where it's triggered simply by sight and smell of food, where the signals are traveling from the brain through the vagus nerve. Once again, go revisit the autonomic nervous system mini lecture from last time. But next we have the gastric phase, which is activated when food actually enters the stomach. And then we have the release of of gastrin, which is a hormone from the stomach. Then finally, and arguably the most important, we have the intestinal phase. That's the most significant, because this is where we actually have the release of other hormones like cholecystokinin, CCK, and other responses as the food is coming into the small intestine, where a lot of digestion is happening and then all of the absorption. Interestingly, there's an interplay here, as I alluded to earlier, where endocrine hormones influence this process. For example, insulin supports acinar growth and enzyme synthesis. So the acinar are the area, that's the part of the exocrine pancreas, the production of the digestive enzymes. Well, insulin helps those cells maintain their function. Somatostatin actually restrains enzyme secretion. It prevents them from being released when they shouldn't be released. And then pancreatic polypeptide also plays a little role. So we have this really interesting dialogue where we have these three canonical endocrine characters, insulin and the pancreatic polypeptide, the somatostatin, each playing a part to regulate the degree to which the exocrine pancreas interacts here. And we do see disrupted communication in disease. For example, I noted pancreatitis. Pancreatitis damages exocrine cells, but it will often lead to diabetes because of collateral damage to islets. the islets of Langerhans, the endocrine part. Conversely, in diabetes, the lack of an insulin production and insulin's effect can lead to exocrine atrophy. Remember how I said how insulin helps keep those exocrine cells functioning? Well, what if you aren't making insulin or you don't have enough in your pancreas? Then you can start to atrophy those exocrine cells. And so you're not going to have enough of those digestive enzymes being produced. So the practical lesson here is, to me, lifestyle habits can directly affect both sides of the pancreas. If you have a diet that is high in refined carbs and you're putting a burden on or less effective production of insulin, disrupted production of insulin, let's say, no surprise that you might start to have disrupted function of the exocrine side. But in contrast, if you can help keep the endocrine side working well with a proper balance of insulin and glucagon, then you can also help the exocrine side continue to work well, helping you maintain an ideal process of digestion and better gut health and overall better nutrition. So I hope as I wrap up, I've convinced you that the pancreas is, in fact, a metabolic multitasker, and there's nothing to compare to it, where when you consider the endocrine hormones, they are regulating nutrient metabolism and energy balance, but you also have the exocrine products that ensure we can actually get those nutrients in the first place, where we digest and absorb those nutrients. The two systems are inseparably linked, of course, not only in function, but in anatomy too, where it's all coming from one single organ. And if one part of the organ is suffering, no surprise that the other follows. Remember, there is direct communication between the two as the blood is flowing. By understanding and supporting the balance through diet, exercise, and other just rational, smart lifestyle choices, we protect not only digestion, but also, of course, the entire metabolic function of the body. Until next time, more knowledge, better health. Looking to improve your own metabolic health? Visit InsulinIQ.com for courses, coaching, consultations, and a 10-day free community membership trial. To dive deep into the science behind metabolic health, become an insider at benbikman.com, where you'll enjoy my exclusive content, ad-free podcasts, live stream Q&A access, and more.